C.3, prove Fibonacci formula. So now it is the time to do this proof. We are ready. We did a lot of preparation. So now finally we get to this point. All right, so we are ready to apply mathematical induction. So I hope you can understand, the complexity of mathematical induction. We used this method once before. Remember the logarithm, that log formula, right? It's pretty complicated. So now another time. First, we need to make mathematical induction. We need to make induction assumption. All right, Assume the formula is true for k in the range. Lower bound 2, higher bound just some positive integer n. Okay? Certain positive integer n. So although lower bound we know for 0, 1, 2, 3, all correct, right? So 2, we put a 0 is okay. 0, 1, 2, 3, all okay, right? All right. We have this expression. Now, our goal, we need to verify fn plus 1. Plus 1. The upper bound plus 1. So that's the key step in mathematical induction. Upper bound plus 1. You go one step forward. You can still prove it's true, then the mathematical induction will guarantee that the whole formula is true for all positive integer n. Okay. All right. Formula transformation. Still, we need to do appropriate formula transformation. Okay. All right. Let us work on this formula. This must be true, right? Because this recurrence relation given from the original question. So this must be true. Then look at fn minus 1. They both satisfy the condition for the induction assumption. The subscript falls into the given range, right? The subscript n minus 1, subscript n minus 1 falls into that range, so we can use induction assumption here. The first induction assumption, we have this expression. Second induction assumption, we have that expression. All right. Now let's do some term combinations. Rearrange terms. Here I put the, polynomial terms or monomial terms. Monomial terms together and the fractional terms together. Why I do this? So you may ask me why I do this kind of transformation. The reason is simple. The idea is simple because we want to put the terms with similar structures together. The terms with similar structures, monomial terms, they have the similar structures, right? Fractional terms, they have the similar structures. So we like to put them together based on their structures. All right, next, guess and verify. Remember, the guessing part is very important. If we can make good guess, then we can do a lot of things very fast. Here we make some appropriate, suitable guess. All right. So now, when we make the guess, so when we make the guess, so you compare fm plus 1 expression and the fm plus fm minus 1 expression, they should be the same, right? 1 over root 5, we don't worry, right? 1 over 5, just same constant. Two things with the same constant, we can ignore 1 over root 5. Then, the part inside parentheses should be the same. All right? Then, the part inside parentheses has two groups based on the structures. Monomial terms, fractional terms, right? Can we, in our guess, the monomial terms part, similar structure, that part should be equal. Fractional structure part, they have the similar structure, they should be equal. That's our guess, reasonable guess. Okay, so our guess should be like this one. Phi to the n plus 1 equals phi to the n plus phi to the n minus 1. That's the monomial terms comparison. Fractional terms comparison, we have this one. But that's the guess part. We need to verify it. So in our next slide, we will verify these two formulas, correct or not. If correct, we prove it. All right, so let's do the work in the next slide. First, let's prove the relatively easier formula. Monomial structure, much easier to handle, right? We start with property of golden ratio. So we need to work on this property directly, because this one you can see if your eyes very sharp, you can connect immediately, because if we multiply both sides by phi to the n minus 1, we get our destination formula. So we verify it. Correct. One simple multiplication, correct. Okay? Step 1. Step 2, this time, a little harder. We need to work on the fractions. A little harder, but still not too hard. We can handle. So let's work on it. With denominators, we know that denominators could cause complexity problem. Complexity. So we want to remove denominators by multiply common denominator of all the fractions. Common denominator. What is the common denominator of all the fractions? Phi to the n plus 1. That's the common denominator of the three fractions. So this time we use another commonly used mathematical technique. We call it backward thinking. Backward thinking. In order to prove the current formula, we need to go one step backward. We only need to prove this version. This version, how do we get this version? Multiply common denominator, both sides. You just multiply phi to the n plus 1, both sides. Left-hand side, denominator is gone. Right-hand side, First term, you have a phi. Second term, you have phi squared. That simple. Okay? Yeah, so backward thinking. Yeah. But after that, we feel that negative 1 to the certain power, yeah, still pretty annoying, right? We want to remove. Pretty annoying. Yeah. So this time we multiply negative 1 to the n minus power. In this way, you can see we completely remove the negative 1's power, the annoying part, right? To get a clean, short expression that is 1 minus phi squared minus phi. This happens to be one of the properties of golden ratio. We derive it. So 1 can be represented as phi squared minus phi. We derived it before, so here we just use it. And we are sure this is correct. Then, by backward thinking, the previous formula is correct. Another backward thinking, this one is correct. Then combine all 4 correct formulas. We get the final Fibonacci formula correct. Yeah. So that's the whole proof. Look at this. That's the whole proof. Yeah. Think about if you can follow. Yeah. Pretty complicated. So we did a lot of mathematical development. Think about it. If you can completely understand all these steps. All right, so we finish part C.3.